You know the world you live in? It wasn't just found like this, it was built. Intentionally. From the water that comes out of your tap to the bridge you drive over on your commute, there's this invisible layer of design that shapes just about every moment of your day. So today, we're going to make that invisible engineer visible.
I mean, really think about your morning. You turned on a tap and bam, clean, safe water. You drove to work on a road that didn't crumble. You're probably sitting in a building right now that stands firm against the pull of gravity. Ever just stop and wonder, how? How does it all work? Well, it's definitely not magic. It's civil engineering. And our whole journey today starts with that simple glass of water.
So yeah, our investigation starts right here. We're going to trace that single drop of water all the way back from your tap through this hidden underground world of pipes and treatment plants to uncover the science that makes our modern lives even possible.
This is where environmental engineering comes in. It's this really crucial part of civil engineering that's all about a delicate balancing act. Keeping us safe from the environment, but also keeping the environment safe from us. It's the science behind the clean water we drink, the fresh air we breathe, and what happens to all the waste we create.
And right here, you can see the sheer scale of the challenge they're up against. As a city grows, the demand for water just explodes. So for a small town, an engineer might plan for, say, 110 liters per person per day. But for a huge metropolis with over 1 million people, that number triples to more than 350 liters. And that's not just because of more people. It's more industry, more infrastructure, a whole more complex way of life. Engineers have to see this coming decades in advance to build systems that won't fail us down the road.
But here's the thing. It's not just about the quantity of water. It's all about the quality. And to figure out how polluted water is, engineers turn to chemistry. They use concepts like biochemical oxygen demand, or BOD. To put it simply, it's basically a test of how much oxygen the tiny organisms in the water need to break down all the gunk. A high BOD, that means you've got really polluted water and a much, much bigger job for the engineers.
And for every single drop of clean water we use, we create a brand new problem, wastewater. Now, get this, roughly 80% of the water piped into our homes and businesses goes right back out as sewage. This creates a whole other engineering challenge. It's like a mirror image of the clean water system, all designed to collect, treat, and safely return that water to the environment.
So that final step, actually getting the water into your home, is a huge design puzzle. On the one hand, you have the grid system. It's great for older cities. It keeps water moving so it doesn't get stagnant, and if a pipe breaks, it's no big deal. Only a small area is affected. On the other hand, there's the ring system. This is perfect for newer, more planned-out areas. It means water can get to you from at least 2 different directions, so there's no single point of failure. The one they choose depends entirely on the city's bones.
Okay, so we've seen the invisible systems hiding inside your home. Now let's step outside and take a look at the engineering that gets you from point A to point B. Let's talk about the science of your commute.
We just take it for granted, don't we? But flying down a road at 100 kilometers an hour in a 2-ton metal box, that's actually pretty dangerous. So how in the world do engineers design roads that let us do this relatively safely every single day? Well, it all comes down to a mix of physics and, believe it or not, human psychology.
2.5 seconds. That's it. This one number governs almost every single aspect of highway safety design. It's the official perception reaction time. It's the window engineers give an average driver to see a hazard, realize it's dangerous, and actually move their foot to hit the brakes. Every safe stopping distance, every sign you see, it all starts with this number. And that 2.5 seconds is the absolute key to this formula. The total distance you need to stop safely, what they call the stopping sight distance, is really just 2 things added together. First is the lag distance. That's how far your car travels during that 2.5-second reaction time, before you even brake. Then you add the braking distance, which is how far the car actually skids once you've slammed on the brakes. The engineer's job is to make sure you can always see at least that far ahead.
Hey, ever notice how you don't get violently thrown to the side of your car when you enter a curve on the highway? Well, you can thank transition curves for that. Instead of just snapping from a straight road into a sharp curve, the road actually eases you in. It starts with a curve that's almost straight, and then it gradually gets tighter. This gently introduces that centrifugal force, the one that wants to pull you outward, keeping your ride smooth and, most importantly, keeping your car on the road.
And what if your commute takes you over a bridge? Chances are you're crossing a truss, which is that classic web of triangles. The design is just genius in how simple it is. As a car drives over, the top beam gets squeezed together. That's compression. At the same time, the bottom beam is getting pulled apart. That's tension.
The diagonal beams transfer all those forces through the whole structure. It's the simple fact that triangles are incredibly rigid that makes the whole thing work, creating a super strong but surprisingly lightweight bridge.
So we've gone from the systems that bring us water to the roads that carry us, and now we're going to shift our focus down, literally, into the earth. Let's look at the science of building all our structures on solid ground.
You know, it's a question that sounds almost ridiculous, but it's one of the most fundamental challenges in all of construction. We're putting millions and millions of kilograms of steel and concrete onto a simple patch of dirt. What in the world stops the whole thing from just sinking?
The answer is a whole field called geotechnical engineering. This is the science of understanding soil, rock, and the very ground beneath our feet. Before any big project even starts, these are the engineers who drill deep into the earth, they pull out samples, and they run tests to figure out exactly what they're building on top of.
A lot of the time, the natural ground just isn't strong enough, so engineers have to improve it. On the left, you've got compaction. Think of heavy rollers literally squeezing the air out from between the soil particles. It's a really fast process. On the right, you have consolidation. This is where a heavy load is applied for a long time to slowly squeeze the water out. So one is about air, the other is about water, but they both have the same goal, to make the ground dense and stable enough to build on.
And underpinning, well, everything we've talked about so far, from bridges to buildings to the soil itself, is this fundamental relationship between stress and strain. So stress is the force that's pushing or pulling on a material. Strain is how much that material bends or stretches or deforms because of that stress. The entire job of a structural engineer, really, is to design a world where all the everyday stresses never cause a strain that leads to failure.
Okay, we've looked at the nitty-gritty details and the foundations. Now let's zoom out. Let's just take a moment to appreciate the sheer, massive scope of what civil engineering actually accomplishes, building the very lifelines of our civilization.
And this is where you see the true scale of the impact. I mean, we are talking about airports that connect entire continents, dams that power cities, tunnels that carve right through mountains, and harbors that welcome global trade. These aren't just construction projects, you know? They're the physical operating system for our whole modern society.
And the work of that environmental engineer comes full circle, right? It extends from the water under our feet to the very air we breathe. They're on the front lines, measuring and finding ways to reduce air pollution, helping to set and enforce the strict health standards that you see right here. It's just another one of those invisible layers of protection engineered for our well-being.
All right, so we've seen the what and the how. But to wrap things up, let's just touch on the final piece of this huge puzzle. How do these massive, incredibly complex projects actually get done?
See, building this stuff isn't just about math and physics. It is about masterful management. Every single project follows a life cycle. First, you have meticulous planning, where every single detail is designed. Next comes controlling. That's the constant monitoring of money, schedules, and materials during the actual construction. And finally, there's updating, because, no plan ever survives contact with reality. It's this living, breathing process that turns a blueprint into a building that lasts.
So the next time you turn on a tap or you drive across a bridge, just take a second to remember the invisible engineer. Our world didn't just happen. It was designed. And, that brings up the ultimate question. The engineers of the past built a world to solve their challenges. So in our age of rising seas, extreme weather, and superconnected cities, what kind of world must the engineer next? Thanks for watching.